Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a topic on minor losses of energy in pipes, or we can say the minor energy or head losses when it is flowing through a pipes. In our previous lecture, already we have discussed about the major losses. So there we have seen the major loss is to happen due to the friction, and we have studied there and how to find out the losses also we have derived. So actually the loss of head or energy, both we can say, the loss of energy or head due to friction is known as major loss. But while coming to the minor loss, actually, in the minor loss, we need to consider the velocity mostly. Okay. The loss of energy, you can say the loss of energy due to change in velocity. Due to change in velocity. Okay, when the fluid is flowing, if suddenly the velocity of the fluid changes, and in terms of in magnitude and direction, that is called as minor losses. So this minor losses used to happen. Few regions are there, or some cases are there. What are the cases we can call as a minor losses? So let me write the loss of head, or the we can say the loss of head, the loss of energy. We can call it as a loss of head, or we can call it as a loss of energy. Loss of head due to, first point, sudden enlargement. Sudden enlargement in the pipe. This is one point. Okay. Second one is this all will be same. Loss of head due to sudden contraction. Yeah. Next is the loss of head, again. Loss of head due to not due to, you can say the loss of head at the entrance of pipe. At entrance of pipe. Entrance of pipe. And similarly, next one is the loss of head at the exit of pipe. Entrance and exit of pipe. Next is fifth one, I can say the loss of head due to, here again, due to obstruction in the pipe. Due to obstruction in pipe. Now similarly, again we can say the loss of head due to bend in pipe. Bend in pipe. And the last one we can say the loss of head due to fitting, various fitting in the pipe. Various fitting in the pipe. So these are the some regions are there for the minor losses. So one by one we'll see in our lectures all these losses. So in this lecture, let's discuss about the loss of head due to sudden enlargement. The name itself, we can identify that where suppose a fluid is flowing with a particular diameter, and suddenly the diameter of the pipe was increased to some another diameter, then what is the loss of head will be there in that particular point. So for that, here I have taken, so this is a pipe is there, and this pipe is having a some diameter d1. So here the diameter d1 is there, and suddenly the diameter changed to another diameter. Yeah, and this diameter, suppose d2 is there. So due to the changes or due to the sudden enlargement of this pipe, what is the loss of head or what is the loss of energy in the fluid, that need to be discussed here. So let's consider the fluid is flowing through this pipe with a velocity v1, and it is moving through a pipe of this initial pipe, and suddenly it was changed to this one. And let's consider two different sections in this pipe. This is section 1, this is section 1, and this is another one. Like after enlargement, the two sections need to be considered, before enlargement and after enlargement. So before enlargement, like section 1, and after enlargement, so let's consider this is section 2. Why I'm considering this section 1 and section 2, that also I'll explain. Actually here we are considering two different sections because we know that when there is a fluid flow over a pipe and or through a pipe, we need to consider the Bernoulli's equation. So we need to apply the Bernoulli's equation in the fluid flow. Now, so at the section 1, if you see, a few parameters are there which are related to this section 1. That means a smaller diameter. Now see, this is the pipe is there, and through this pipe we have a diameter d1, and the fluid is flowing with a velocity v1. Okay, now suddenly this pipe changed to a bigger diameter compared to the previous one, and this diameter is suppose like this. Okay, now when the fluid is flowing through these, we can see that in the diameter d1 how the fluid is covering all these layers of this pipe. Okay, it is, see, after changing or after enlarging the pipe diameter, the fluid cannot cover up all this, surface area through the pipe. So the fluid will be moved, like, it will create its own path, like it will go like this, it will move like this. Okay, so few part will be neglected here. So this part you can see, so this part will be not covered by this fluid flow. Okay, and that's why here some eddies formations will be there in this corner part, because this part is not covering by this fluid flow, and due to the sudden enlargement, so that's why here this area will be not covered under the fluid flow path. Okay, and when the fluid is flowing through these, okay, few of the fluids, you can say, few of the fluids are coming out from their own path. Like, see, this is the path of the fluid, how the fluid is moving. Okay, now when the fluid is moving, it cannot go like in this to this corner, then again it will come like this. It is not possible, correct? Because that is not the nature of the fluid, how it should path, how it should flow through the pipe. So the fluid will continue, or the fluid will choose its own path. Okay, like this it will move. Okay, and here also same thing. Now in pipe 1, or you can say the at a diameter d1, the fluid will cover up all these paths through the pipe, but while changing its diameter, suddenly it will move its own path like this. So it cannot able to cover up this zone. Okay, this area. So that's why few of the fluid particles will come out from their own path, and they'll form in a eddies formation here. Here some fluids particles will be come out from their own path, and they'll form some eddies. So this is called eddy formations are there. Okay, now so let's do the derivations for this. As I told you that section 1, section 2, so at this section 1 we can say the pressure intensity P1 we can consider at this point, the pressure intensity at the section 1, and the velocity V1 is there, and the area of the pipe at the section 1, that is A1. Okay, and due to the sudden enlargement of this pipe, again in the section 2 we can consider P2 is there. Similarly, P2, the pressure intensity at the section 2, and V2, the velocity at this point, section 2, and the area of the pipe changed. So all these things, if you see, these are the three things are there. Now one thing I'll tell you, see, we know that the equation A1 V1 equal to A2 V2. So this is the continuity equation. As per this continuity equation, we can you can assure that when the velocity and area of the pipe are both are related. That means here area is, if A is less, velocity is less, means your velocity will be more. okay, and your pressure will be also less. But when it is coming to the second section, at this section, you can see your area is more. Here, A2 is more. So A2 more means your velocity V2 is going to decrease, change. But here pressure P2 is going to be increased here. Because all are related. This is area velocity relations. After that, from this Bernoulli's equation, we will get the relations of velocity and pressure also. Anyway, so these are the two things, two various parameters at the section 1 and section 2. Now, due to the sudden changes, as I told you, there is some eddies formations are there. The liquid flowing through the from smaller pipe to the larger pipe actually, and it is not able to properly follow the changes. So that's why when the boundary changes, initially this is the boundary, now the boundary changed to here. This boundary was neglected, and due to that, some turbulent eddies are formed, and that eddy formations, that is the main reason or the causes of loss of energy. Okay, and here this eddies also, this eddy formation which was formed here, that also will be give a impact, or that will be give a pressure, okay, on the fluid flow. So that will be a F-stroke type. So that is also one pressure will be there. That is, you can say the intensity of pressure in the eddies on the area. Which area? See, everyone, some area is there. So pressure intensity at this one, section 1, pressure intensity at the section 2. So here also the pressure intensity, let consider P dash. Let consider P dash, the pressure intensity of this eddies liquid on the area. Which area? Now this is A1 area, this is A2 area, and this part, actually this part is, which is not considered, that one we can write the area, the larger area minus smaller area. So that was the pending, like means area which is not coming in contact with the liquid flow. So this one we can consider. Now, what is the loss of head? So the loss of head, let's consider HE. HE is the loss of head due to sudden enlargement. Loss of head due to sudden enlargement. Now, when I have considered these two sections, let apply the Bernoulli's equation in this flow at the section 1 and section 2. So we can write P1 by, here we can write rho g, though the same liquid is there, so let's consider only rho. So no need to consider this rho 1 and rho 2, all the things. So you can just write V1 square by 2g. This is the Bernoulli's equation, already you have derived previously, and this is Z1 equal to P2 by rho g. Again, this is V2 square by 2g and plus Z2. Then after that, what is the losses happened? So that is the loss of head due to sudden enlargement, that is HE. Okay, so this is the equation of Bernoulli's, which we have already derived previously. Now we can see pressure energy or pressure head, and this is velocity head, and this is datum head. So this datum head or potential head we need to consider. Let consider a line. So this is our datum line. So this line is suppose fixed, and this datum line what we have considered, we need to find out the Z1 and Z2. At the section 1, what is the height of this from the datum line? So this is Z1. And the section 2, at this point, what is the value of this datum head? So that is Z2. So you can see both Z1 and Z2 is same for this pipe flow, because the pipe is horizontal. So we can consider Z1 and Z1 equal to Z2. So now we can write Z1 equal to Z2, where the pipe is horizontal. Also you can write, for horizontal case we'll get the same thing, Z1 equal to Z2. So now we can write the same thing, like we can write this equation P1 by rho g plus V1 square by 2g, and Z1 Z2 same, so leave it. Now again P2 by rho g plus V2 square by 2g plus HE. Now this is pressure head, pressure and velocity in terms, then we need to find out the head loss. So let's write the head loss due to sudden enlargement. So what we'll do, we'll keep pressure one side, like pressure one term, that means P1 minus here will come. Let consider this equation in this side. So that means P1 by rho g minus P2 by rho g bracket close. Again plus we can write here v1 square by 2g minus v2 square by 2g. So this is equation, let's give equation 2. Okay, what about the equation 1? This one you can give equation 1, the Bernoulli's equation, what we have already derived previously. Now from this equation and 1 and 2, like see the head loss we have identified in terms of difference of pressure energy and or pressure head and velocity head, we can say. Now we need to consider again, because there is a eddy formations are there and there is some losses are there, so we need to consider that part also in this derivations. So for that what we will do, we will consider this eddies formation, what is the pressure intensity is there in that point. So for this is the term, the pressure intensity at this eddy portion and the area, the pressure intensity at that particular area. So what I'll write here, now let's consider suppose this is the control volume of, this is the section 1 and section 2, and this, let's consider this control volume, and the force acting on the liquid on the control volume. See what is the force is acting here. Now you can see this is the force is acting P1A1. Why this is P1A1? Now we know that pressure equal to force by area. So at the section 1 I can write F1 equal to what the force acting at that point, P1 into A1. Similarly at the section 2 I can write F2 equal to P2 into A2. Okay, now let's consider, as I told you, the force acting on the liquid on the control volume of this section 1 and section 2 in the direction of flow. In the direction of flow is nothing but x direction flow. So I can write this Fx equal to, I can write P1 A1 minus P2 A2. Now one more force is there, that is this one, P dash and A2 A1. That means here also the pressure intensity due to this eddies formation, so there is a force will be occurred here. So that one we can write in terms of, this is minus, okay, not plus. This is the minus one, and this one will be plus P dash, because in the direction of flow is there. So you can consider this is A2 minus A1. Now let here the P dash value and P1 value, this P dash value and this P1 value, this both the pressure intensity are same. Okay, because just it was here. See, if you see, you can ask us, just now you told that if the area velocities are changing, the pressure also changed. Yeah, it is correct. But when it is changed, you can see that means the changes are happening here at this point. The changes are happening fully changed at this point when it is the area is fully changed. So that by experimental it was found that the P dash value and the P1 value both are same. So if this is the case, then we can consider Fx equal to P1 A1, and this is, we can write again P1, just elaborate this, P1 A2 minus P1 A1 plus P2 A2. Now you can see, you can cancel this, I hope. This P1 A1, you can cancel it. So remaining what will be there? P1 A2 plus P2 A2. Now we can write Fx equal to, we can take common of this A2, so that we can write P1, and this will be, I hope, minus, yeah, P1 minus P2. So this is P1 A1. Okay, this was minus actually. Sorry, this is minus. That's why I'm confusing. This is minus. This is not plus. Okay, P1 minus P2. So this one we can give an equation 3. So this is the value of Fx. Okay. Now what we need to find out? Next we need to find out the moment, or the momentum of the liquid. So let's go to the next one. So let's find out the momentum of liquid at section 1 So momentum equal to, we know that mass into velocity. So mass into velocity, we can write mass, we can write rho a v1, rho 1 a y v1 into the velocity. What is the velocity at this section 1? That is v1. So we can write this is nothing but rho 1 a1 v1 square. Okay. Similarly, we can write the momentum at section, momentum of liquid per second at section 2. Similarly, same thing we can write. This will be rho, no need to write rho 2, sorry. Same rho a2 v2 square. Okay. Now this is momentum at section 1 and momentum at section 2. Then what about this change in momentum? So the change in momentum, we can write change in momentum per second, change in momentum of liquid per second. So this one we can write this equation minus this. That means rho can be taken common, and here we can write this is a2 v2 square minus a1 v1 square, bracket close. But we know that from the continuity equation, as I told you already, a1 v1 equal to a2 v2. Okay. So from here we can write a1 equal to a2 v2 by what? v1. So now in this value, if we put, because here see a2 v2 a1 v1, 4 values are there. Let consider in a single term. Okay, let make it a1 or a2 or v1 or v2, like this one single term. Let convert this. That means here I have taken a1 equal to a2 v2 by v1. Now again, what I'll do, I'll just put this value, okay, a1 equation here. This is the a1 equation. I can put the value here. Let here. After putting the value here, so what we'll get here? Rho, let's write in details, rho a2 v2 square minus, here again rho, in place of a1 I can write a2 v2 and divided by v1 into v1 square. So v1 square will be cancelled, only v1 will be there. So that one we can write rho a2 v2 square minus rho a2 v1 v2. Now we can take common of rho a2. A2 is common. So a2 common means we will get v2 square minus v1 v2. This is another equation. I hope equation 4. Yeah, 3 completed. Now this is equation 4. Now here, as we have seen that the force acting on the control volume in the directional flow, that should be equal to the force, the rate of change of momentum. So we can write, we know that force equal to m into a. So the force which we got previously, that should be equal to this. So the force what we got here, Fx equal to a2 p1 minus p2. So let's write as per the equation. You can write that is what, a2 into, here it is p1 minus p2 equal to, here it is there rho a2, and this is v2 square minus, sorry, v1 v2. So this is the equation. Now what I can write here, I'll just take this rho in this side, and let me write p1 minus p2 by rho, and this force, sorry, this is p2 pressure. No, this is a2 area is there. So area a2 can be cancelled here. So what will be there? Rho I have taken to this side. Now this side, in the right hand side, v2 square minus v1 v2. So let divide the g in the both side. Okay, let divide the g term in both side. So you can write this is g, and here also you can get g. Now here, if you separate this, we can get it P1 by rho g minus P2 by rho g equal to, we can write this equal to V2 square minus V1 V2 by g. So this is the equation what we got. Now previously what we have already got this equation in terms of, yeah, this one. What is the head loss? Because finally we need to find out what is the head loss or what is the loss of energy due to the sudden enlargement. So this equation we already got previously. Yeah. So let's put the value of P1 minus P1 by rho g minus P2 by rho g. Which one? This one. Let's put the value of P1 by rho g minus P2 by rho g. That means this one. In which equation? Now in this equation. So let's put this value. So this one will do one thing. Equation 5, let it. So put the value of this in the equation 1. So we can write HE equal to, let's see once, this is HE, this is the pressure difference value. So the potential head what is there, we can write V2 square. So let's write V2 square minus V1 V2, this one divided by G, and this plus V1 square by okay, remaining thing is as usual, like V1 square by 2G and minus this is V2 square by 2G. This is the normal equation. Now see, G are all are there in the denominator. So what I can write here, let keep in this denominator G 2G. So 2G means here again 2 will be multiplied. That means 2 V2 square minus 2 V1 V2. Again 2G already there in the denominator, so no need to change anything. So it is V1 square, again it is V2 square. Now if you see, this term is there, 2V2 square minus V2 square. So that means here I can write, this one I can write V2 square minus 2V1 V2, 2V1 V2 plus V1 square divided by 2G. Okay. Now if you see this equation, we can see if you want to consider this A square B square minus 2AB. So this one we can write A minus B whole square. So finally what I can write, HE equal to V1 minus V2 whole square divided by 2G. This is the head loss due to the sudden enlargement in the pipe, and this is our final equation. I hope you understand. Here what I've done, just how I've written, let me write here again, like I have written V2 square, and this is V1 square plus V2 square minus 2V1 V2 divided by 2G. That means A square plus B square minus 2AB. So that is A minus B whole square. So this one just I have directly written here. So I hope you understand this derivations of the loss of head due to sudden enlargement. Still, if you are having any kind of query and doubt regarding this, you can give a comment on the comment box. Thank you all.